So, summer packet number 6. So number 6 says find the value of this messiness that we see here for each of the following functions. Now, this has a special meaning when we get into the calculus of it all, but right now we're just focused on the algebraic portions of it. So we're not going to talk about the meaning of it just yet, but just the algebra, the substitution that we experienced. Number 5 is very similar with number 6, just a little bit different, but same idea, substitution. So number 6 here says find the value.
Okay. So we just plug it into the x.
Right. Well, let me walk through what this is going to look like initially. Okay, so this is what we're trying to do. We're trying to find a representation for that f of x plus h minus f of x. Oh, and by the way, is my voice coming through okay?
Yes.
Okay, all right. So I want to make sure it wasn't muffled. Okay, so here's part A. F of x is 3x plus 7. Now, we're substituting this expression into this, this value into this expression here. So we have a substitution for this f of x, right? So this f of x is just going to be this 3x plus 7. So that's pretty easy.
Okay.
But the question that that issue that we have is trying to find a substitution for this f of x plus h. Okay, so let me show you how we could do that. If f of x is 3x plus 7, then f of x plus h means we're going to replace every x we see with an x plus h. So what I tell students to do is pretend like we don't know what's inside the parentheses, and you replace the 3x plus 7 with a set of parentheses. So that means any argument that goes in here is going to go in place of the x, but I created the space for it. So therefore, now if I wanted to do f of x plus h, is simply 3x plus h plus 7.
Okay.
So from now on, if we ever want to make that substitution, I always like to tell students, hey, create the space for that value, and then you're not going to make a mistake because now you know exactly where it's going to live. It's going to live inside the parentheses.
Okay.
So now this, let me highlight what we're going to do. This piece will replace this, and then this 3x plus 7 will replace this f of x.
Okay.
So now what will this look like?
So that's going to look like 3x plus h plus 7 minus 3x plus 7.
Okay. Is there anything special that we have to anything that we have to watch out for when we put the 3x plus 7 here?
Oh, should we put parentheses in front of it because of the negative, or?
That negative, right. That negative is always going to cause an issue if there's multiple terms that comes after it. So.
Okay.
All over h.
Okay.
Okay. So now all we're going to do is just clean this up, and that's all. We're not going to go into what this means just yet. It's the algebra that trips a lot of students up, so we want to take the time to practice that.
Okay.
Okay, keep going. Any other like terms that we can do here?
The sevens.
Hmm.
So 3x h. And then the 3x's.
Mhm.
That's 3h over h. Is that as far as we can get it, or can we cross out the
Yeah, we
h's?
can cancel it out, yeah, because there's nothing that's added to this term that's preventing us from reducing, so we can get it all the way down to 3.
Okay.
Okay. Part B. You want to try talking through this problem and
Yes.
using
Okay, so
part A as a
oops,
guide?
sorry.
Yeah, go ahead.
Okay, so let's see, 3x. So this is just saying anything. Okay, so this is the same as part A. Okay.
Yeah, same.
So we know the just the f of x.
Mhm.
We can just plug in the 3x.
Yeah, all this is going to go here.
Right. Okay, so the f of x can go into that, but then with the is it going to be the same thing where we take 8x plus h and we plug it into all the x's?
Exactly, yeah. So maybe you don't do this every time if you can see it, but I like to just, let students know that, if they're having trouble seeing it, if they can get it to look like this, you're not going to make a mistake because
Right.
you have a spot for where all those x plus h is going to go.
Yes. So 3x plus h squared minus 2x plus h plus 1 minus, in parentheses, 3x squared minus 2x plus 1 over h.
And you put parentheses around the
Yes.
fx. Okay.
Yes. So now we can simplify.
Mm-hmm.
Okay. Can we expand the x plus h squared?
Yeah, good. So that has to take precedence before this 3 is even worked into the parentheses, right? So
Right.
good. We can fold this out.
Okay.
Maybe I'm taking more steps than needed, but I want to show everything here.
Yes. So that would be 3 times x squared plus 2hx plus h squared minus 2x plus h plus 1 minus 3x squared minus 2x plus 1.
Okay.
And then we can distribute the 3 and the 2, right?
That's right. Now all the parentheses can be resolved all at the same time here.
Got it. Okay. So 3x squared plus 6hx plus 3h squared minus 2x minus 2h plus 1 minus 3x minus, minus 3x plus 2x minus 1.
Mhm.
Okay. Well, our 3x squares minus 3x squared, those can cancel out. Negative 2x plus 2x can cancel out. 1 minus 1 can cancel out. So we're left with 6hx plus 3h squared minus 2h over h. Can we factor that?
Yeah.
So 3.
What's the factor, common factor that we can take out?
H. Oh, and 2, right? No, because there's a 3 in there.
Just H, yeah.
So 6x plus 3h minus 2 over h. Can those two h's cancel out?
There we go, yeah.
Because I don't think 6x plus 3h minus 2 can simplify any further, right?
They can't. That's as far as we can go. Yeah, we'll talk later what this means, but it's the algebra that trips a lot of students up. So I'll take care of all this first.
Okay.
Okay, part C.
Okay, so same thing as A and B. We know our f of x is going to be equal to 6 over x, and our f x plus h is going to equal 6 over x plus h.
Good. Yeah, you don't have to do what I'm doing here, but for some students it is helpful to have that previous step there.
Yes.
I think what a lot of students want to do is they want to put the plus h out here after the expression, right? But it's gonna, but if you, we need to leave it inside the parentheses, which is what we did. So good.
Right.
Okay.
Okay. So now we have 6 over x plus h minus 6 over x.
All over h.
Oh, right.
So this is a little messy because we have a complex fraction, right? We have a set of fractions underneath a larger fraction. So the strategy here is we're going to take care of this piece first. Find a way to clean this up.
Okay.
The way we're going to clean this up is we're going to try to merge these two fractions together. But if I want to add or subtract fractions, to find common denominators.
Right.
Okay, so we're going to step to the side and try to work on this problem here. So now the question is, before I can merge these together, I need common denominators. What do you think is a common denominator for these two fractions?
X? I don't know.
Right, so it has to be something large enough that both can multiply into.
Oh.
It has to show characteristics from both these denominators.
It'll be x squared plus hx?
Yes, so because we can't just say x plus h because x is not the same as x plus h. So if I have two completely different denominators, I need both of them to create my common denominator. So I'm going to leave it in factored form, but that's exactly what you were saying.
Okay.
So your common denominator is always going to be larger, usually larger than each of the individual fractions. And so now we got to balance, right? We got to ask what's different between this denominator and this denominator. We see that this new denominator has something extra that this doesn't have, right? And it's
another
the
x.
So,
so we would have to make that 6x.
That's right. I need to, because this denominator needed an x to get to my new denominator. My numerator needs an x to match that same process.
I see.
And what's changed between this old denominator and this new denominator?
They've added x plus h, so you have
Yep.
to add x.
I need to include an x plus h for my numerator as well.
Okay.
Now that I have common denominators, I can merge all this into one messy fraction.
Right. Okay.
Okay, so let's continue cleaning this up. Leave the denominator alone, but we are going to try to clean up the numerators a little bit more. So what would that look like? Oh, let me just give perspective here. This whole thing is now all over h.
Okay.
All this work that we did is just the numerator, but we've pushed it together, and this will make merging these two a little easier. But let's get this part cleaned up first.
Okay.
Okay, distribute the -6 through.
Okay. Oh, I see. Okay.
Anything we can clean up here?
Huh?
Is there anything that we can clean up here? Or any like terms that you see?
Oh, we can do 6. So 6x minus 6x would be 0.
Mm-hmm. Now look at what we have here. It's a little bit better than what we had before, because before we had two separate terms, but now we've combined it into one term, and now dividing by this h is the same thing as multiplying by its reciprocal. So I'm going to bring that h up.
Okay.
So now it's going to be dividing by h is the same thing as multiplying by 1 over h. See that? I flipped that h
Okay.
to the top. But basically, I'm doing this. I'm doing times 1 over h times 1 over h. And I know that this will just go away because I multiply by the reciprocal.
Okay.
Now, if I want to put all this under one fraction, I can. Do you see anything else that we can do to clean up?
Can we distribute the x?
We could, but I'm thinking in terms of, is there anything that we can take away?
Oh, we could take away the h's, right? And then be -6 over x plus.
Yeah.
X times x plus.
Yeah, so here, you can leave it in factored form or you can distribute through. It really doesn't matter, but this is pretty much as far as we can go in terms of removing things from this expression. So this is fine, or -6 over. But typically, with these problems, we'd like to keep it in factored form, but either would be acceptable.
Okay.
Okay.
Got it. Wow. Okay.
Yeah, it's a lot, right?
Yes.
It's a lot to practice through those fractions.
Oh, yes.
Okay, let's
Okay.
look at 7. Okay, for the piecewise function, find each of the following. So piecewise function just means that you have two parts of a graph that normally would conflict with each other, meaning that two graphs that are overlapping each other. And if they overlap each other, we can call it a function. But if we cut up the function where it's only showing to one side of an x value and the other side of an x value, then the two graphs are going to look weird, but it's not going to fail the vertical line test because maybe a graph that looked like this. I'm just making it up here. Like square root of x plus 4 is maybe something that's like this. And then x minus 5 squared, maybe it's something where it's picking up, maybe somewhere over here and it's going over like that. Right, so like we're cutting up the graph so that it will not conflict over each other. Right, so something like this. But it says find each of the following. So it says, where's the graph living at -3? Where's the graph living at 0, at 5, and at 10? So we should have to be able to insert the x value into the appropriate piece. But the way that we decide is we look at the restriction. Is the x value to the left of my restriction, or is it to the right of my restriction? Right. Anything that's less than 5, I want to use this expression. Anything that's more than 5, I want to use this expression.
Oh. Okay. So for A, since it's P is -3, I would use
x,
root
right? If x is -3, right? Yeah, you would use the first one, right?
Oh, and I just plug that value into the x part?
Into the x, yeah. This is the x value that you're inserting either into this first x or the second x. But the way you decide is you look to see where's that x located.
Got it. So -3 plus 4 is -1. So that means square root of 1 is 1.
Yeah, good.
Is it just +1 or plus or minus?
Just +1, right?
Okay.
We only these are principal values. The only time you have plus or minus if you're trying to solve an equation If you have to introduce square root into both sides of the equation, then you have to worry about plus or minus.
Okay.
But if it's just the expression itself, and if you're not introducing square root into the equation, then it'll always just be a positive version of it.
Okay. So B, since x is 0, we're going to use the same equation, x plus 4 root of 0 plus 4 equals root two.
Mm-hmm.
Okay. See, it's P5. So this one I'm going to use the same thing again.
Yeah, because that equal sign.
Right. So that's root 3. Not root 3, that's just
root
3.
9.
Root 9 and then 3. Okay. And then D is P is 10. So I'm going to use my x minus 5 squared, just 10 minus 5 squared, which is 5 squared and 25.
So now we're going to write these absolute value functions as piecewise functions. Walk through this here.
Yeah.
Okay, let me start off with an example here. So here's an absolute value function at its most basic form. This is a parent absolute value function. And its y is equal to the absolute value of x. Now, what this graph looks like is this. Looks like a V, and that V is centered at 0.
Okay.
Does that look familiar to you?
Yes.
Okay. So the idea is that, okay, this is the absolute value function, that's fine. But what if we rewrote this as 2 linear graphs and 2 lines that happen to be cut off at 0? So, let's say, what if I thought of this line as continuing and this line as continuing, but I'm purposely cutting off these 2 line segments, so it's only showing me this part. And then if I were to create 2 lines graphs that have restrictions, then I can kind of create a substitution for this function. But it would look the exact same. So
okay.
Imagine we want to create this line here. So this line is basically y is equal to x, y equals x, because the slope of 1. Okay.
Mm-hmm.
That goes through 0. So this, if we put this graph, this line segment in slope-intercept form, it'll be y is equal to 1x, because the slope is 1, up 1 over 1, and then plus b, so plus 0, because the y-intercept is 0. So just 1x.
Oh.
So
Okay,
does that make
so
sense that this graph here is just 1x?
yes.
Okay. But it's not, if I just say 1x, that's not completely accurate because 1x would continue on in both directions.
Okay.
But I'm purposely going to stop the graph at 0 because if I let it continue, then this will create an x, and x is not a function because it won't pass the vertical line test. So I'm going to say I'm only going to show this graph to the right of 0. I'm going to cut this part out.
Okay. Oh. Oh, I
So
see.
basically, what I've created so far is I've created this.
Okay.
So now I need to create the other side of it because this graph is also can be rewritten as y equals mx plus b. But now what's the slope of this line?
Same thing.
Okay, but the
1x?
slope is, what's the slope?
Oh, negative 1x.
That's right, it's down 1 over 1, right?
Right.
And the y-intercept is still 0.
Yes. So that would be negative 1x, comma, x is greater than 0?
X is less than 0.
Because it's on the other side?
That's right, because we only want this negative 1x to live to the left of the y-axis. So that's going to be this graph. So we've created the picture of this absolute value function, but we're using linear graph to make it duplicate the picture of this graph.
Okay.
Now, there's one other thing that we need to do is we need to define this vertex somewhere. Because right now, if we just left it in this form, there's going to be a big gaping hole at 0. However, these graphs are both meeting at the same point. So it really doesn't matter where you put the equal sign. You could put it here, you could put it here. Just choose one, and that will get the full picture.
Okay. Wait, I only choose one of those?
You only choose one of these. Yeah.
Okay. So I could choose just 1x, comma, x is greater than or equal to 0?
Right. Or you can also write it this way. These will do the exact same job.
Okay.
You're basically just asking one of these graphs to fill in that hole.
Okay. That makes sense. So would that mean for this one?
So one thing that that I still want to talk about is the fact that it's easy to see where this vertex is. It just kind of makes sense that it's at 0. But really, the way you want to find that restrictive, location of that vertex is you're always going to set what's inside the absolute value bar set equal to 0. If you set the portion inside the absolute value bar equal to 0, that's always going to locate the vertex for you. And if you can find the vertex, then that's going to be where the dividing line is going to be. That's where the graph is going to shift from one graph to the other.
Okay.
So here's number 8.
Okay.
Y equals absolute value of 5x plus 2.
Okay, so that would mean
Let's find the vertex. So we're going to set everything inside the absolute value equal to 0. And solve for x.
Okay, so 5x plus 2 equals 0. 5x equals -2. X equals -2 over 5.
There we go. So that's where, instead of 0, now we're going to be splitting on either side of -2/5. So here's our setup. Now, the way we decide which expression goes here, basically it's just going to be either a positive or a negative version of what's inside the absolute value bar. So there's going to be a 5x plus 2, and there's going to be a negative 5x plus 2.
Okay.
Now, you may not know exactly where this graph lives, but the fact that there's no negative sign in front of the absolute value bar means that this graph is going to be a V opening up.
Okay.
If there was a negative in front of the absolute value bar, that means the graph is going to look more like this.
Okay.
But it's positive, so it's going to look like this. Okay.
Okay.
Now, 5x plus 2, is this a positive slope or a negative slope graph?
That's a positive slope.
Positive slope. And the positive slope, is it to the left or to the right of my vertex?
To the right.
To the right, which means I'm going to say x is to the right of -2/5. Because that's my vertex.
Right.
Which means
and then
that
since that one's a negative slope, it's going to be x is less than negative
or
2/5.
in other words, to the left of my vertex.
To the left.
Yeah.
Okay.
And then
either one of those can have the equals.
Just don't put it in
right?
both. You can choose either one.
Okay.
And then here's something that we could do if we want to clean this up a little bit more. Go just a little bit further. But this wouldn't be wrong. Just want to kind of give you some other looks.
Okay.
Or if I want to switch this up, I can.
Okay. So either one of those would work. Okay.
All right, let's look at part B.
What does that 8 mean?
Okay, so that 8 is not going to affect the way that we look for the vertex. It just means that the graph is shifted up 8 units, but it's not going to impact how we find the vertex. The vertex is the x value of the vertex is just going to be what's coming from what's inside the absolute value bar.
Okay.
But that +8 is still going to be a part of my expression that I write here.
Okay.
But I'll show you where that +8 is going to come into play a little bit.
Got it.
Okay, so is this graph going to open up or down?
This is going to open. Oh, this is going to open down because that's a -4x, right?
Right, but it's still a positive absolute value, yeah. So
right. Okay.
There's a little bit of strangeness to this, but that's going to come later. You're looking at what's outside the absolute value. if it's positive, then this is going to live completely above the x-axis.
So that will live above because it is
Yeah, it's a little
positive.
above. Now, if there was a negative in front, then that's going to show you it's going to open down.
Right.
Okay, so it's good to kind of have this visual, so we have a picture as to what this graph will look like. Okay, now let's find the vertex.
Okay, so we have to set that whole thing equal to 0?
Just what's inside the absolute value bar. That's the only place you gotta look.
Okay, I got 3/4 equals x as my vertex.
Okay, so we know that is this dot right there.
Yes.
All right. Okay, we'll create two versions of my two linear graphs. One will be the regular version of my expression. And the other will be the what?
The negative version.
Yeah, but it's only negative around this parentheses. Okay, the negative is not going to impact the 8.
Okay.
Okay.
So it should be for the top one, x is to the right of 3/4.
Now look at this here. Now we got to look at this a little more carefully. I know we haven't cleaned this up yet, but is this expression going to be a positive or a negative slope?
Oh, that one's going to be a negative.
Yeah, so that's where that negative is going to be a little bit strange because the regular graph is the regular piece linear is not going to be the one on the right. It's going to be the one. It's going to be talking about the one on the left.
Okay.
So this is going to be x is what?
Less than or equal to, which is to the left.
That's right. Less than 3/4. Which means that
and then
or to preview this negative distributing through, this is going to be a what? Positive or negative slope when everything is set. Positive slope, right? That imagine that negative coming through. This gives us a positive 4x. That positive 4x indicates it's going to be talking about this side of the graph.
Right.
Which is to the right.
Okay.
And we'll do a little bit of cleanup here. We're going to just combine like terms, distribute the negative, and just do a little bit of, go a little further just for practice purposes here.
Okay. So that should be negative 4x plus 12.
Plus 11.
Oh, yes.
Okay.
Sorry. And then 4x minus 3 plus 8 is 4x minus, no, 4x plus 5?
Yeah.
Is that as far as it can go?
Mm-hmm. Good.
Okay. 9.
All right. 9. Let's skip the parts that I don't find as important. Let's do number 10. 10A.
Okay.
I was going to show 10A here. All right, so 10A says, determine the domain for each of the following. The way you find domain is you simply look at the denominator. Whatever makes the denominator 0 is where the restriction is going to occur.
Okay. So do I just plug in numbers or?
Okay, so to find domain restrictions, set the denominator equal to 0 to find vertical asymptotes or holes that breaks that we have to remove from our domain.
Okay.
So we're focusing purely on just the denominator. Don't have to worry about the numerator, at least not for these rational functions.
Okay. Okay. Oh, so we set it to 0?
Mm-hmm.
Okay. Now we can factor?
Yep, go ahead and
Is that
factor.
right? Okay. So we should have 2x minus 3, x plus 2.
Okay, let's multiply to be -12. That's 1. 4, -3. Reduce the fraction of possible. 2 reduced to be 2. 3/2 doesn't reduce. Pull the denominator in front. Okay, is that what you got?
Yes.
Okay, so we set each portion equals 0. So we have two separate x values that causes the denominator to be 0. And if it causes the denominator to be 0, that means it's undefined, which means that we can't include these as part of our domain. Because there are visual breaks at these values.
So anytime you have two x values, you can't use them?
Or anytime I have any x values in the denominator, I can't use it.
Oh.
Because if I were to insert -2 into my denominator, I'm going to get 0 overall.
Oh.
And I can't divide by 0, right?
Right.
If I can't divide by 0, that means this point is not going to show up on my graph. It's going to look something like this, where at -2, and at 1.5, there's going to be a visual break in the graph. So maybe the graph looks something like this, where just making it up, but right.
Oh.
So if the graph were to look like this, you could tell, okay, there's obviously a break in my domain. So I have to make sure I restrict it from those values.
Yes. Okay.
So the way we write our domain is we just say all real numbers except for these two values. But the way we write it in interval notation is we say -infinity to -2. We experience a break. And then from -2 to 3/2, we experience a break. And then from 3/2 to infinity. So this is the way that we can say all real numbers except for these two numbers, except for these two x values.
Okay. Is that like a U as in showing it's like?
Yeah, that union is the same thing as a comma. It just means that I'm going to skip to my next interval.
Okay.
But yeah, you
Got
can
it.
definitely write it this way as well. Yeah, either way is successful.
Okay.
All right, let's cover one more part here. Number 11, finding inverse of functions.
Okay.
So here are the
11 part
steps.
A?
Yeah, 11 part A. So here are the steps for finding inverse functions. First step, switch x and y. So every time you see an x, you replace it with a y. Everywhere you see a y, you replace with an x.
Okay.
And then once you do that, then you solve for the new y that you see.
Okay.
Okay, so we start off with 4x minus 3. F of x equals 4x minus 3. If you see f of x, that's another notation for y. So just to make it easier, let's say this is y equals 4x minus 3. So let's follow our steps.
Okay.
What will this look like after I take step 1?
Okay, so that's going to be x equals y squared 4 minus y squared.
X equals just 4y minus 3.
Oh.
So I'm just literally just making a clean substitution. Everywhere I see a y, replace x. Everywhere I see an x, replaced with a y.
Oh, whoops. I accidentally my eyes accidentally went to 12A instead of 11A.
Oh, I got it. Okay, got it.
Yeah. Okay, so it's 4x minus 3. So y equals 4x. So x equals 4y minus 3.
Okay, so that's what we have after our first step. Now we're going to solve for y, because y now is mixed into the equation.
Yes. Okay. So do I try to get y by itself or?
Yeah, get y by itself.
So we can make it x plus 3 equals 4y. And then x plus 3 over 4 equals y.
Yeah.
Oh, is that the answer?
Yes. We call this the inverse function. And so the inverse function is obviously going to look a little bit different than this. And we use this notation, this f inverse of x, to indicate that we've created the inverse function.
Oh.
So these have a special relationship with each other because everything is flip-flop. The domain is flip-flop, the range is flip-flop. So the domain for this will be the range of this, the range for this will be the domain of this. So what happens is, anytime you see a function and its inverse, they're always going to have this picture about it. They're always going to x minus 3. Okay, so I'm not graphing this exactly yet, but the idea is that the two graphs will always going to be foldable over this diagonal line y equals x, because everything is flip-flop. The y is the x is the y. The order pair will be flip-flop. If there's an order pair 1, 3 here, then there can be an order pair 3, 1 here. So that's the relationship that we're going to see. But right now, we're just doing it algebraically to get from one function to its inverse. Right, let's see if we can go through parts B and C as well, following the same steps.
Okay. So B is g of x is 2x plus 3 minus 4. Y equals 2. Okay, so x equals 2y plus 3 over y minus 4.
Okay, it doesn't look like it's easy to get y by itself because there's multiple y's, right?
Yeah.
But let's do this.
Right.
Why don't we maybe cross multiply first, and then we can kind of sort through this mess.
Okay. So x times y minus 4 equals 2y plus 3. Do we need to distribute the x with the y minus 4?
Yeah, let's distribute all that, and then maybe we can group the y's together. Okay. A little bit more algebraic work here.
It's going to be xy minus 2y equals 4x plus 3.
Mm-hmm. Why don't we put the y's together so we can factor that out?
Okay, so that would be y x minus 2 equals, or 2 minus x. Oh, because when I guess I... Wait.
That's fine. You moved everything to the other side, which means that your answer will be the negative version of mine, but I want to show that we're on the same page, even if you're on the other side. So keep doing it your way.
Okay. So I have y x minus 2, 4x plus 3. Y equals 4x plus 3 over x minus 2.
Okay, so this is my version, right? Your version is right?
Yes.
Do you know why these are the same?
Is it because like your numerator is like -3, -4, and mine's the positive version of that, which makes the bottom the same?
So basically, I can get to your version, and you can also get to my version if either one of us multiply the numerator or denominator by -1.
Oh.
Right, because if I multiply the numerator and denominator by -1, I'm not changing anything. It just looks a little bit different. So my sign is exactly different from yours, but they're off by a factor of, both are off by a factor of -1, but that's really the same thing as multiplying by 1.
Okay.
So we're really at the same stage. It's just a little bit different. So the hint there is I guess the takeaway from this is, if you're on the AP exam and you get to your answer, and your answer is this, but the solution, the answer choice is here.
Yes.
You know, you're thinking to yourself, wait, my answer doesn't look exactly like the answer choice, but maybe if I were to multiply this by -1, both top and bottom, the answer that I'm looking for can suddenly appear.
I see.
So just because your version is not in the answer choice doesn't mean that you're wrong. It just means that you have a slightly different variation of the correct answer. So you may have to do a little bit of rearranging to make it look like the answer choice.
Okay. Got it.
Now, having said that, this does look a little bit cleaner because there's less negatives. So if it was on the AP exam, chances are they would have this version over this one. So if I landed on this one, I'll be able to get to this one just by playing around with the signs a little bit.
Okay.
All right, last one here.
H x equals so x minus 1 equals y cubed. And now we have to get rid of the cubed.
Swap the x and y. Yeah.
Right. So when I swapped it, sorry, I got x equals y cubed plus 1.
Okay, good.
And then I got x minus 1 equals y cubed.
Okay.
I'm a little stuck, though. I don't know what to do with the cube.
Right, so how do we undo a cube? Take the what at both sides?
Cubed root.
Cube root, yeah. So cube root will do the job of undoing the cube.
Okay. Oh, so that's going to be y. And y equals -1.
Y equals cube root of x minus 1. Now we can't resolve this because there's a minus sign in between. So we gotta leave it in this form.
So then we have to do that inverse thing.
Yeah, and it's just write it in the inverse notation.
Okay. That actually isn't too bad.
Yeah, it's a good review through all these pre-calculus and even algebra 2 concepts that we just haven't seen in a while. So next time, figure that we can maybe finish up on the packet. I may skip over some of this. I'll go over the more important things that I feel. Review unit circle. Graphing is not as important, but reviewing trig identities and solving trig equations, I think will be very helpful for us to review. And then horizontal, vertical asymptotes, holes, we'll review that. And then log equations. Hopefully this is more familiar just because this is the last thing that we did, but we'll still review this.
Okay.
And after next session, I think we can get into some of the calculus starting with limits. So, okay, 1 second, let me stop recording. I'm stuck. Okay, that's all right. I will see you next time.
Thank you.
Great rest of your week.
Thank you. You too.
Thanks. Bye.
Bye.